I'm recording. Welcome to Map 721. So what I'll do is I'll record every class, and then like the following morning, I'll upload it to YouTube in case you missed. Okay, so a little bit of background. This is actually a fairly new class, except the number 721 has been in the books for a long time and nobody was using it. But I looked at the description and it's like, oh, there's all the stuff that people should learn about numerical PDEs. And we have so many people in this department, myself, Dr. Chen, Dr. Zhu, Dr. Tian, who research in numerical PDEs. And it's totally insane that we don't have a numerical PDEs class. So I thought, well, that unused number sounds good. Let's use it. So I revived the class in summer of 2017. And the class met for 2 hours a day, every weekday, Monday through Friday, for 4 weeks. And we did the whole course in 4 weeks. And I'm never doing that again. And so then this is only the first time since then that I've offered it as a regular class in a classroom. So I took the topics then that were taught in 20 days and just sort of tried to break it down into what we're going to cover each week. And I think it looks like we will have. Something is weird here with the dates, though. You know what? I think I totally missed next week. I have August 28th. Oh, and then
Labor Day.
Labor Day's no class. Okay, so this week we only have Wednesday, and next week also Wednesday. So what I have under August 28th in the little schedule here is what I can plan to cover between today and next Wednesday. Oh, that's right. And Wednesday's our shorter day. We meet from 4:45 to 5:45, and then we have a full-blown thing, 4:45 to 6:15 on Mondays. Actually, it looks like what I have here, I'll have no trouble covering that in time anyway, between hour today and hour next Wednesday. And then September 9th will be the first full week that we have. Dang holidays. Okay, so, but yeah, this schedule is definitely approximate, because the way this class works, turn to the syllabus now. So I send you all the link to the site where everything is. And I want to point out one weird thing on the syllabus. Under coursework, it says, actually I want to check the site on this to make sure that everything is consistent. It says, the coursework will consist of 10 homework exercises and a comprehensive final exam. Now, I think that I made a mistake and really meant to say 10 homework assignments, but that's not a typo. It really is 10 homework exercises. You know what? It's not 10. It's 7. Because it works out perfectly. You have 7 homework exercises that are 70% of your grade, so 10% each. And the other 30% is a comprehensive final exam. So I am actually giving you literally only 7 problems all semester long, which doesn't seem like much, except those problems are going to be a royal pain in the ass. All except the first one are MATLAB heavy. And so when I ran the class last time, a few summers ago, we'd have some days where I didn't really need to continue lecturing. We just devoted that time. Sometimes it was half a class or sometimes the whole class period, where you guys are just chugging along on MATLAB and I'm able to help, and help was definitely needed. And this works out perfectly with 4 of you. You can pair up or something if you want. So this class is largely about how do we code up certain methods for solving PDEs in MATLAB, and also how do we analyze how well these methods work and so forth. So there's a certain semi-theoretical component to it also. So, in other words, they'll be probably the 7 of the most time-consuming homework problems you'll ever do. So, sort of warning. But at the same time, I chose to be a little bit less ambitious in terms of how much I want to try to cover during this time because, yes, the coding really is a pain, and I probably end up cutting back anyway. So this way, I can stick with a plan. But as far as how much I cover from week to week, that might vary. It just depends. I am going to go through the material in this order that it says here, but I could either fall behind or go ahead a little bit. So, just so you know. Now, on the site, I have on the resources page a full set of notes, like 50-something pages. So that's what I wrote like crazy a few summers ago. So that's what I'm going to follow pretty closely, as I usually do. I want to also mention that this class is based on a course at MIT. So MIT has their open courseware thing where they put all their materials out for everybody. And so when I was preparing this, I found that course first. It's like, oh, this looks like it has everything I want. And I just try not to plagiarize what they had. Well, at the same time, I attributed. So I linked to that from my site, so you can go there and see what they have. I didn't get very far through the topics that they offer, but maybe someday there'll be a second course on that. Okay, the final exam is going to be oral. So some of you have experienced that in prior classes. So I don't know if you did that when you took. Okay, yeah. Okay, yeah. So during finals week, it helps that there are only 4 of you. So we just set up a time where I grill you for an hour or so on whatever I covered. I wouldn't have you writing MATLAB code on the board. That's just crazy. But that'll be it. That's your grade. So okay. So the idea is that after getting through, so if I want to talk about what I'm supposed to talk about in terms of course goals or course objectives or whatever it is they want to call them. So my goal for you guys is after having taken this course, if you then work on to do a research project, whether it's with me or someone else, that involves numerical PDEs, that you know your way around some of the numerical methods, that you can code something up and work with it, and also be able to analyze the results, analyze the accuracy of methods, things like that. And we're only going to cover certain methods in this class, but at least you have enough familiarity to understand other methods as well. So really, it's just a matter of getting your feet wet in what really is a very large, very active, very important area of research enough that so many people, not only in this department, but also in computer science, work on. That we chose as our specialty because these problems are quite a pain to solve. So any questions about the course? Okay. So it'd be a good idea, if you haven't already, to go to the resources page, download those notes. You want to have them to follow along with, as I plow through them. So, okay. So hopefully it'll be fun, as fun as class of numerical PDEs can be. Okay. Now, all of you have different backgrounds when it comes to PDEs, either having just taken them to not taken at all, or maybe it's been a while. So I find it best to assume that everything has been forgotten. So we'll just start from the beginning. Okay. So really, as I go through the first chapter of these notes, I'm not really going to get into the numerical methods at all yet. Yes. It's important to have some idea about just partial differential equations or PDEs in general to be able to and how they might be solved like on paper. We'll look into that a little bit before you understand anything about how a computer would solve them. And then there are certain topics, certain numerical analysis topics that we need that you may have seen in other classes, like solving systems of linear equations, solving AX equals B. A couple of you doubled that last semester in 610. So that's going to be familiar to you. Also, polynomial interpolation or numerical differentiation or integration. So one nice thing about this class is it takes all those topics from numerical analysis classes, all of which you have taken to some extent, and back then they seemed like totally separate things, but now they're all brought together for a common goal, solving PDEs numerically. So that's something that'll be important and helpful for you to see. Okay, so now really all PDEs are equations involving partial derivatives. Of the solution. So the unknown that you're looking for is some function, often referred to as u of function of whatever variables, x, y, z, or t for time. So an equation that somehow relates the partial derivatives of a function that you're looking for, that is a partial differential equation, as opposed to an ordinary differential equation, where you have a function of only one variable, f of x, or u of x, and you're dealing with the first or second or whatever order derivatives of that. So when it's a function of one variable, it's ordinary. With a function of several variables, it's partial. Okay, now some of this stuff is so clear as mud, I wonder if I should even bother with it. Okay. I'll give it a shot. All right. So I want to be able to classify PDEs in various ways. And there are many ways to classify them. But it's important that you know about these different ways so that because certain methods apply, certain solution methods apply to only certain types of PDEs. So you have to know what kind of animal you're looking at. So I'm going to lay down some notation first. Now, so if u is a function, then du refers to, we can think of it as the derivative. So if it's a function of one variable only, it would just be what you know as u prime. But what if it's a function of several variables? Well, then you have several partial derivatives. So partial of u with respect to its first variable, x1. Partial of u with respect to its second variable, and so forth. So we would assume it's a function of n variables altogether. So capital Du would refer to all first partial derivatives. Okay. So you can think of it as a list or vector containing all of those partial derivatives. Now, gold star to anyone who can remember from multivariable calculus, you have this vector of all the first partial derivatives of a function. There's a name for that. What might that be? Okay. Well, it was 5 years ago we took multivariable calculus. Doesn't really understand you not remembering. And you took it 3 years ago. So, Bailey. So, okay. It's a gradient. So now this is a symbol for a gradient. Ring a bell? Okay, hopefully. Well, especially if you took it from me, otherwise I'd be embarrassed. So that's known as a gradient of u. Okay. Now, if I take this to the next step, d squared u. So that's going to be all the second partial derivatives. Now, because we can differentiate twice in respect to any combination of those variables, any xi and any other xj, so here we have differentiating at least once in respect to x1, but then differentiating a second time with respect to all of the other variables, and that fills the first row. And I gotta make this bigger. And then with respect to the second variable and all of our possibilities. And then we keep going. So we end up filling an n by n matrix of all possible second partial derivatives. Now, the ones down the diagonal, that's going to be second partial derivative with respect to the same variable twice. All others is going to be mixed. They're actually called mixed second partial derivatives. All right. Probably setting myself up for disappointment, but now that you guys know, or by jogging memory a little bit, that this is a gradient, that's all first partial derivatives, this has a name also. Collection of all the second part, or a matrix of all the second partial derivatives. I'll even help you out. It starts with an H.
Hessian.
Yes.
That's because I have your notes.
Okay.
No, I won't take credit for that.
Well, good on you getting the notes, though. Yeah, so that's the Hessian of u. Now, this is a good time to use what feels a preferable notation for partial derivatives that you would have also seen in multivariable calculus, because I found it rather annoying to write all these out. But I do want to also make clear, because this seems to come up every time I teach multivariable calculus and deal with partial derivatives, that there's always someone who thinks that when I'm writing these, I'm writing a 2. These are not 2's. There's a partial derivative symbol. So I can't cancel those out. That's a 2 in my writing. So someone always does that. So I just want to quash that right away. So another way, more compact way of writing partial derivatives is that you don't use those partial symbols at all. over those fancy twos. You just, whatever variable differentiate with respect to, you just use that as a subscript. So for gradient to be u sub x1, u sub x2, u sub xn. And similarly, I can write this as u x1, x1, u x1, x2, and so forth. And generally, that's what I'll do. I should mention, I'll go ahead and fill in u x2, x1. And it might seem like we have a recipe for confusion here, where we have u x1, x2, and u x2, x1. But generally speaking, it's not true 100% of the time, but these mixed partial derivatives, we differentiate in a different order. Those are equal. You have to have certain assumptions, like assuming all partial derivatives in question are continuous, which they're generally going to be. So the order which you carry out differentiation doesn't matter. So you don't have to worry about that. In other words, this matrix, so because like these would be equal, these would be equal, it's a symmetric matrix. Okay. All right. Now, I could keep going, have higher order derivatives of u, like the collection of all third partial derivatives, and so on. I'm not going to write, but if a first derivative, that was a vector, and second derivative is a matrix, so what sort of entity, if I went to the third derivative, what would that look like? What? Okay. Well, what? Yeah, that would be a three-dimensional array. So any order derivative, I do like d to the k u, that is a k-dimensional array. Now, those kind of arrays of however many dimensions, people call them tensors. Now, technically, these are tensors also, but everybody calls them vectors and matrices because that's better understood. So that would be really obnoxious to try to write on the board, so I'm not going to do it. Okay. So really, partial differential equations are equations that relate these derivatives of u in some way, that are themselves collections of all possible partial derivatives. Okay. All right. Your suffering for today is half over. So, well, we'll probably do on Mondays. That's an hour and a half. Like have a little break in the middle, but today we'll just soldier on. So, only a half hour left. Okay. So I can use this notation to describe like the most general form of PDE. So general PDE would be some function. So general PDE of order k. Would have, the kth order derivative of u, and then all lowercase, and then u itself, and also x by itself. In other words, you're allowed to have any functions of x that are unrelated to u, could be included in a PDE. So you have some function of your independent variables, your solution, and all of its partial derivatives up to a certain order, k, is equal to 0. Now, a function f could be literally any function of all these variables. So that it leaves you a whole lot of leeway. But there are certain types of PDEs where we impose some kind of structure on the function f that are of interest to us. And it allows us to classify PDEs so we can get an idea of how to solve them, or at least solve certain ones. And it'd be very easy for me to write down a PDE where not only would we have no idea, in other words, nobody on Earth would have any idea how to solve it, or we might not even know if there is a solution. It's not always easy to tell if it does. Okay, so certain types of PDEs, kind of we're dealing with most of the time in this class are PDEs that are linear. Okay. Now, where a function f has this form, now there's going to be some really weird notation. Okay. Now, alpha is not a number in this case. It's actually what's called a multi-index. So, for example, well, let me define it too. This expression here, you might think, oh, it's absolute value, but it's not absolute value in this case. But you can think of this as sort of a magnitude of this multi-index. Is a sum of all the indices in alpha. So a multi-index has n values where u is still a function of n variables. So all of these indices have to be non-negative integers. And what they're meant to do is help you pick out a particular partial derivative of u. So I'll give you an example. Let's suppose that alpha is equal to let's suppose that n is equal to 3. U is a function of 3 variables, x, y, and z. So alpha is this multi-index. First element is 2 and the others are 0. So the magnitude of alpha is the sum of these, so it's just 2. So d alpha u, what this means is we take the partial derivative with respect to the first variable twice. So x1, x1. And then partial derivative with respect to the second and third variables, not at all. So only differentiating with respect to x1. So that's what this notation means. It's a way of picking out a particular partial derivative. So what we're doing is we're looking at a set of terms where you're taking partial derivatives of order up to k. So you can only differentiate at most k times. You take these partial derivatives, multiply them by coefficients, which are functions of only x. So these functions, so these are your coefficients. So what distinguishes a linear PDE as opposed to various nonlinear PDEs, your coefficients are not allowed to depend on u at all. They can depend on x. Your right-hand side also cannot depend on u, only x. So I'll give you an example of a very well-known very well study linear PDE, which we'll deal with a lot in this class. The heat equation. du dt is equal to uxx. So if I want to take this PDE and write it in this form, so it has cycling is equivalent to alpha um, 0, 1. Wait, not alpha. A 0, 1 of x, d 0, 1 of u, plus a 2, 0 of x, d 2, 0 u is equal to 0, where so if I let x be the first variable and t be the second, this is ut. And again, x being the first variable, this would be uxx. And these are your coefficients. So this coefficient is equal to 1. What's this coefficient? So I have to write the PDE so that it's, well, I have no right-hand side function. Everything here depends on u. So that's all on one side. What? Go ahead.
Is it, since it has a right side, you have to move
Yes.
the x over so it's -1?
Yeah. All right. Imaginary gold star for you. Yeah, so I have to rewrite this as ut minus uxx is equal to 0. So the coefficient of ut is 1 and the coefficient of uxx is -1.
Can you say it again when you said earlier that it's linear because it depends on u and not?
No, the coefficients in a linear equation cannot depend on u. Constants fine. They could. I could have had this depend on this coefficient depend on x, like in your honors thesis project.
Right.
Yeah. So, well, and now yours too. So, yeah, but I could not make it depend on u. All right. So I know I've thrown a lot of notation at y'all, so there's a good time to ask any questions. Make sure you have this notation straight.
So you chose alpha to be 0, 1, and then 2, 0 because you knew you wanted it to equal, the coefficient to equal 1 and -1?
Well, these are chosen to match the orders of derivatives that I have in the equation. So that explains why I have these particular multi-indices and no other ones.
How does that represent the order?
Well, if the first index corresponds to x,
Okay.
and the second corresponds to t. So du dt, I'm not differentiating with respect to x, so that's why it's 0.
Right.
I'm differentiating only once with respect to t.
Right.
And then same thing here,
Two
twice with
x
respect to x, not at all with respect to t.
Okay.
Any other questions about this gobbledygook? Okay. Actually, yeah, for the most part, we're dealing with linear PDEs. And maybe even where coefficients may be constant. That's always a good starting point. Even though in my work I deal with variable coefficient PDEs. But you got to start somewhere. Okay. So that's one classification as linear. And then just kind of move up from there, making more and more general. we have semi-linear. Okay. So for that, it starts out the same way, where you have coefficients that are allowed to depend on x but not u, times whatever partial derivatives of u you want to include. But then the rest of the equation depends on any lower order derivatives. This is important. Here, the derivatives can go up to order k. This is a kth order equation. But I may have a function that depends on lower order derivatives of u, and also just u itself and x. So here we have like a nonlinear part, but the highest order part, that can go up to order k, is still linear. So, so it's just one step removed from linear. I have a bunch of examples of PDEs here. Let's see if any of them fit that category. Actually, apparently not. Well, oh, yes, I do have one. We'll work with two variables in space, uxx plus uyy is equal to u squared. That's a semi-linear PDE. Now, this expression right here is very important. When you have a sum of all of the second partial derivatives where you're differentiating with respect to the same variable twice, so x twice and y twice, but no mixed partial derivatives. This is called a Laplacian of u, which has various notations that you might be familiar with. So here we have a gradient symbol squared times u because it's second derivatives, also written as like this. Because here you have a gradient of u, but then we have this dot with a gradient symbol again. This is something called in multivariable calculus also. Div, or divergence. So the divergence of the gradient of u happens to give you this, and that's the Laplacian. It is also written this way. It's using the delta. Okay, so, and yeah, I've seen all of these notations very commonly used, unfortunately. So here we have this function. So f of u is equal to, well, the way I've written it, minus u squared, because I moved it to the other side. So that's an example of a semi-linear PDE, where part of the highest order derivatives is linear. Then we have this nonlinear term because it's u squared. If I had just u by itself, that'd still be linear. But anytime you start to take any nonlinear function of u, squaring, or taking a sine or cosine or exponential, anything like that, or square root, that's what makes it nonlinear.
Why did you make u squared negative?
Oh, because the way I wrote the equation here, I had everything on the left side, but this is here on the right side.
Does the Laplacian actually have a third dimension, or like?
Well, it has however many dimensions that u is a function of. So like if I had u of x, y, z, I'd have a uxx plus uyy plus uzz. So this is a 2D Laplacian.
So then the uzz is there, but it's 0. Or do you just not?
Well, yeah, it is. That's right. Because if u is a function of only x and y, its derivative with respect to z would be 0 anyway.
Right.
Yeah. Okay. So questions about a semi-linear case. Okay. So then Go to quasi-linear. So in this case, still same kind of summation, but now your coefficients are also allowed to depend on lower order derivatives of u, or it can be functions of x. If you have another function f that's not multiplying any derivative, so that's the step from semi-linear to quasi-linear. In semi-linear, the coefficients were only allowed to depend on x, but now they can depend on u or its derivatives. So one of the best known examples of a quasi-linear PDE, Berger's equation. So that's ut plus ux is 0. Okay, so this is a first order PDE because all the partial derivatives are at most first order. So I can think of this as A01 D01 of u for ut plus A10 D10 of u equals 0. So this is ux, and this coefficient is u, and this coefficient is 1. So the coefficients are now allowed to depend on u and derivatives, but not of the highest order. That's so that part's still not allowed. So if I have a second order PDE, I can't have uxx as one of my coefficients. So that's a quasi-linear. And then if we have a PDE that doesn't fit into any of these baskets, I should number these. That is called a fully nonlinear. So those are the worst kind.
When we did the linear, like then here we have A01, why is it there and X?
Okay. I'm not sure what you're asking.
Yeah, I'm not either.
Okay.
Well, I was looking back at when we did this with the heat equation.
Oh, okay.
Like when we translated Berger's equation into the notation, like A,
Yeah.
1. I was looking at when we did that with the heat equation, trying to see if I was following.
Oh, okay.
But there's no, like the coefficient that represents 1, it's not a function. Or it's not.
Well, it's always allowed to be a constant. So the coefficient can be as simple as you like. It's just that once any of the coefficients depend on something other than x, like it depends on u, that's what makes it not quasi-linear, or certainly can't be linear anymore.
Okay.
I'm not sure if that answered.
Oh, I need to look at it.
Okay. All right. So if coefficients depend on anything up to x, like they could be constants, functions of x, that's linear. The moment any u dependence sneaks in there, depending on where it pops up, then either semi-linear or quasi-linear. Certainly not linear anymore. Like, let's suppose that, let's see. Suppose I had UTT instead of UT. So that's a second order. Well, any U dependence in coefficients, or any so this, if I had UTT, that would not be quasi-linear, that would be semi-linear. Because any nonlinearity was in a lower order term. Okay. But here we have a first order PDE, and we have U dependence in the coefficients of first order terms, which are the highest order terms. That's quasi. So then, the simplest definition of fully nonlinear, none of the above. You cannot classify it as linear, semi-linear, quasi-linear. That's fully nonlinear. An example of that is called the iconal equation. So I'm just going to write it out in 2D, where we have the magnitude of the gradient. Now, the magnitude of a vector, a gradient is a vector. Magnitude of a vector is a square root of the sum of squares. So in this case, that would be square root of ux squared plus uy squared is equal to 1. So that's the iconal equation. So because we have that freaky square root going on here, well, actually, even if I didn't have a square root, let's suppose I squared both sides. So then I have ux squared plus uy squared is equal to 1. Well, that still does not fall into the quasi-linear basket, because if I thought of this ux squared as ux times ux, so one of the ux's is a coefficient, and the other is this. Well, the coefficients, quasi-linear coefficients not allowed to depend on the highest order derivative. It has to be only lower order. But that doesn't happen here. So that's why, even if I square both sides to get rid of a square root, it's not quasi-linear. Okay. So, questions? All right. Now, everything described here is for a single PDE. You'd have systems of PDEs. So I could have several unknown functions, U, V, W, etc. And so if I have like 3 unknown functions, I would have 3 PDEs that can relate all of them. So you have 3 PDEs that are coupled together, and they form a system. Now, I do have a definition here in the notes for a system that is. You thought this was cumbersome, and ugh. And actually, I'd taken this definition from the MIT course, and they said something wrong in it. So I'm not touching that one. But I will write down, we have it here. Okay. An example of a system. The shallow water equations. Okay. So it's a system of 2 equations and 2 unknowns. So U is one unknown, and H is the other unknown. H refers to height or depth for modeling fluid flow in shallow water. So with ocean modeling, you have to take all three dimensions into account, but with shallow water, it basically allows you to take one dimension out of the problem. So we have two equations and two unknowns. So dHdt plus u times h with respect to x, so derivative of product is 0, and then we have udt plus ux is equal to minus g hx. I think g is probably gravity. So these equations are coupled. You can't just solve one and then substitute that solution into the other one. Because here we have u and h both involved in the first equation and in the second equation. You have to solve them together, which is a huge pain. I don't know if we'll be doing systems much in this class, but that is something that comes up in my research now and then, dealing with systems. Well, a lot of the very important PDEs are systems, and you can't always pull those equations apart. Okay. Oh, the hour's up. It's 5:44. Okay. Well, that worked out pretty well. Well, I actually want to check the schedule here. I'm supposed to, by the end of next class, get through well-posedness. I have other examples of PDEs to talk about, but it looks like I'll easily be able to do all that next Wednesday, so we will not be behind. So yes, you've suffered enough for today. I'll have this video up sometime tomorrow morning.